All right, I'm gonna check to make sure this thing's on. Audio check, audio check. Hello, hello, hello. Good. All right, so today I'm doing a lecture on the computer, so you can watch it on Edmodo. It is currently May 3rd, 2013. We are doing this on How Solutions Form, the handout that you've received. Now, my pen ready. All right, so this is section 15.1 in the textbook. Here's the outline of what we're going to talk about today. Types of solutions, the first one. What are the different types we have? How are they made? Second thing is, how do we make them? Making of solutions. Third is how it works. Like, how does this happen? What occurs that makes a solution occur? Also then, the rate of reaction, how fast it dissolves, how slow it dissolves, and what affects that, which is related to the experiment we've did yesterday, as well as, the experiment we did yesterday. All right, also temperature and pressure. We'll talk about how that affects solutions, specifically how temperature and pressure affect the dissolving rates of specific things that are being dissolved. All right, so types of solutions. Here we see several pictures. On the top left, we have seawater. Next to it, we have a picture of brass. Brass is a solution, seawater solution. We also see down here in this picture some sodas. Those are solutions as well. And then a picture here of the approximate composition of air, which air happens to be a solution as well. So a solution is a homogeneous mixture, where particles of the mixing substances are evenly distributed throughout. So solutions are homogeneous, therefore they are evenly distributed. Homogeneous is, by definition, the particles are equally distributed throughout. Okay, next slide. 3 classes. We have solid, liquid, and gas types of solution. If you look at the pictures on the right, think about which one would be the solid form, so the final state of the mixture. Which one's the solid? The answer is the brass is the solid. That's brass. I'll write that down for you. Brass is a solid solution. The water in the ocean, that would be a liquid solution. So this is liquid. Brass, that is solid. Liquid is like sea water. And then if you look at this one down here, that's a liquid as well, since we can drink it. It's a liquid. And then the air is therefore the gas solution. Okay, so salt water has 2 different pieces, solids that are mixed in and liquids. The liquid is water. The solids are various things from salts to basically anything we put in, that's in the ocean. There's lots of stuff in there, including sand. Soda, we have a liquid combined with a gas. So the gas is dissolved in liquid. Here we have solid dissolved in liquid. Air, we have gases dissolved in each other. In bronze, we have a solid. I believe it's copper. Dissolved in, combined with zinc or Zn. Hopefully that's, let me see, make sure that part of the screen is on the, yes it is, good. All right, so copper plus zinc. I think that's what brass is, I'd have to look. So that's bronze or brass. Okay, so we can mix different kinds of things together to make solutions. We have 3 classes, solid, liquid, gas, and we can combine various things to make those solutions. Now, to make a solution, we take a solute and dissolve the solute in the solvent. Here you see a container, right? Container of some kind, with some kind of liquid in it. And the liquid in this case is the solvent. Which kind of solution would this produce? Would it be a gas, liquid, or a solid? Correct answer, this would be a liquid solution. All right. Oops. So solutions are produced when one substance is dissolved in another. So one substance is dissolved in another. That is how we make a solution. Now, in a solution, we have several words that are important. Solute. It's the substance being dissolved. The substance being dissolved. Example being if I add salt to water, usually what we say is the salt is the solute is what's being dissolved by the water. All right, the solvent is the substance that dissolves the solute, so dissolves the solute. So in this example, salt is the solute, water is the solvent, because it is the thing that dissolves the solute. All right, generally, the substance present in the largest amount is the solvent. So if I put a lot of salt into a little bit of water, we would change those roles, and the salt would be the solvent, the water would be the solute. Now, question. What is the solvent in air? I said earlier that it was a solution of gas with gas, right? So it's going to take a gas to be the solvent. Think about what you might expect it to be. I'll give you 10 seconds to think about your answer. Write it down in this space here that I put the box around, and then we'll move on to the next slide. All right, so the actual composition of air is 78% of it is nitrogen, 21% of it is oxygen, and then we have somewhere around 1% that is carbon dioxide, argon, water vapor, and other gases. So what is the solvent? Solvent in air is the one that is most prevalent. And so, hold on, I need to pause this. All right, so the solvent in air is the one that's most common, nitrogen. So nitrogen is the solvent. Write this down on your page, by the way. It's part of the assignment. The solute, which is the one we are dissolving in the solvent, is the one that's less common. So there are several. There's all these things listed here. These are all the solutes. Oxygen is one of the main solutes. There's a lot more of it than some of the others. We also have carbon dioxide and argon and nitrous oxide, various other gases, some helium. And so the solutes there are many different types of solutes in our normal air, but the solvent, since it's the most common one, is nitrogen. All right, so how does dissolving work? In this picture on the right, you'll see several things. We have these shapes. Those are, as listed here, water. Okay. Then we have this central piece here. Let me see if I can draw some circles around it. This piece here, that piece is glucose. It's essentially is sugar, the stuff that we dissolved in water yesterday and the day before. These red and white sections attached to the sugar are called hydroxyl groups. It's the chemical name we have for them. And then this interaction between water, so the interaction here between water and these hydroxyl groups is called a hydrogen bond. So why does sugar dissolve in water? Is the question. Write down the answer you think is best in the space provided. I'll pause here, take a couple of minutes to write it down, and then you continue on the next page. So write your answer to this question here. All right, so the answer is because water and sugar are polar molecules. When we talked about polar versus non-polar in class, we said polar where was a situation where the electrons were not spread evenly. So the electrons were not spread evenly. That is a polar molecule. The other one, non-polar, is when the electrons are spread evenly. Okay, so both of these are polar. Both the glucose and the water are polar. Their electrons are not spread evenly. As a result, they interact with each other and can dissolve each other. So these polar molecules, we can also say they have a positive and negative area. I suggest looking at figure 15-2 on page 418 in your textbook. It shows how a sugar clump could be broken apart by water. Look at that figure for a little bit, see if you can understand how it works. It will help you understand the dissolving part. Now, one thing to remember, there's a phrase you'll need to remember is like dissolves like. If you have something that's polar, it will combine with stuff that is polar. If you have a molecule that is non-polar, it will combine with things that are non-polar. So, like dissolves like. Moving on, dissolving rates. What can you do if you want to speed up the rate of dissolving? We have three options: solid and liquid, solid and solid, gas and liquid. Here are your words. You need to take these words and write them next to your column. So write the words in here. I'll give you a few minutes to try that on your own, and then I'll give you the correct answers. We're going to put your answers here, and then the correct answers. Oh wait, correct answers are going to be on the next page. So just put your answers here. You're welcome to pause if you would like some more time. Moving on to the next page. So, solid and liquid, talking about the dissolving rates of solids in liquids. If we stir the solution, this brings more fresh solvent in contact with more solute. And so, if more solvent comes in and interacts with more solute, it means that it will happen faster. So this is, stir the solution will increase the rate, increase the speed at which it's being dissolved. Second one, grind large crystals into smaller ones. This greatly increases the surface area. Okay. Recall dissolving takes place at the surface of the solid. So dissolving only takes place at the edges, and if we make more edges, so dissolving occurs at the surface. If we make more surface, it will therefore increase the rate. So increase the rate of dissolving. So third one, increase the temperature of the solvent. This speeds up the movement of particles, okay, and therefore more solvent particles bump into the solute. You imagine our sugar molecule or our sugar clump sitting there. If more solvent molecules come in and steal sugar molecules away, if it happens more often, then the sugar is going to dissolve faster. So if more molecules, solvent particles, bump into the solute, this also increases the rate. So those are your three things that increase solid liquid solution rates. Stirring the solution, grind large crystals into smaller ones, and increase the temperature of the solvent. All right, next slide. In gas and liquid solutions, things are a little different. Shaking and stirring does the opposite. So it exposes more gas to the surface, and therefore this decreases the rate of dissolving gas into liquid. You may ask why on this. Well, it's kind of like saying if when we had solid in liquid, we were wanting the solid to be interacting with the liquid more often. And if it did that, then it would dissolve faster. In this case, it means you're bringing the gas out of the liquid, away from the liquid, and as a result, the gas is not dissolved in the liquid as much. It all depends on what you decide is the thing you're dissolving into, in this case liquid, whereas in the last case we were dissolving into liquid as well. However, the gas in this case leaves because it is coming out of the liquid and not interacting with it as much. I'll answer more questions about this in class on Monday. This also causes temperature to increase slightly. So temperature increases. This also decreases the rate of dissolving gas into liquid. This causes gas to come out of the solution, which is the same thing as saying this decreases the rate of dissolving gas into liquid. And as a result, the soda goes flat. The soda doesn't have the carbonation anymore, and if you leave a soda out for a while, it doesn't work well. It's flat and doesn't have the carbonation that we like. So, how do temperature and pressure then affect our solution and dissolving rate? What happens to the pressure when you open a bottle of soda? Write your answer in blank. A second here. However, on your diagram, on your page, make sure you leave space to write in what my answer is. So, your answer, and then the teacher's answer. All right. Do that for each one of these, and then I'm going to, and then actually pause the video at this point, fill in your answers, and then in a few moments, once you have done that, come back and fill in my answers to the questions. So, you will have these categories on here. Right. And so here's my answer to the first question. What happens to the pressure when you open a bottle of soda? The pressure in the bottle in the bottle, let's say specifically above the liquid, decreases. And the reason I think this is because more bubbles of gas come out of the liquid. So if there's less gas above the liquid, the pressure decreases. More bubbles will then come out of the gas and come out of the liquid and into the gas area above the liquid. So what happens to the gas inside? Specifically, what happens to the gas inside let me clarify this. The the bottle is what I wanted to say. So what happens to the gas inside the bottle? My answer is it escapes into the air outside. All right, which will lose fizz faster, a cool soda or a warm one? The answer is a warm soda. If you look back at this slide, notice it says increased temperature will decrease the rate of dissolving gas into the liquid. So a warm soda will lose fizz faster because the gas does not stay dissolved in the soda. It leaves the soda and goes into the atmosphere. So warm soda, because the gas escapes the liquid faster, and yeah, just because the liquid, the gas escapes the liquid faster. All right, so to kind of summarize that again, in the opposite way, if we decrease the temperature, so decrease the temperature, it will cause the gas to dissolve in liquid faster. It's the opposite of what we said earlier. Decrease the temperature, gas will dissolve in liquid faster, versus increased temperature. So it's increased temperature, gas will dissolve slower, versus decreased temperature, gas will dissolve faster. Okay. If we increase the pressure, it will keep the gas dissolved. So if I take a 2-liter bottle of soda and I pump more air into the top of it, it will keep the gas in the liquid. But as soon as I open the cap, you've done this, especially if you've shaken the thing, you'll see that it just kind of fountains out because the pressure inside has become less. So this is increased pressure, keep the gas in the container, whereas in liquid, increased pressure, a larger amount in liquid, decreased pressure, a smaller amount in the liquid. So if I wrote a similar thing for this upper one, this would say decrease temperature, increase amount in the liquid, amount of gas in the liquid. If I increase the temperature, I decrease the amount in the liquid. All right, so that's how temperature and pressure affect the dissolving of gas in liquid. Now, one thing you need to know is solid and liquid solutions, solid and liquid solutions are not affected by pressure. At least not very much. They're not really affected by pressure, but gas and liquid solutions are. All right, so conclusion. A solution is a homogeneous mixture. Homogeneous mixture. Homogeneous meant the same throughout. Solutions can be any combination of solid, there's supposed to be a comma there and a comma here, solid, liquid, and gas. We can combine solids with liquids, solids with solids, solids with gases, gases with liquids, gases with solids. All of those are possible. Solvent is the substance present in the largest amount. Remember the phrase like dissolves like. This applied to polar dissolves polar and non-polar dissolves none. Sorry about the poor handwriting. All right, if we increase the temperature, it increases the dissolving of solid in liquid. Solid in liquid. Please add those two words there, otherwise the sentence doesn't make a lot of sense. Increased temperature means a decreased dissolving of gas in liquid. So that is all for the lecture. Good luck at filling it out. Fill out the things I've added to it, and I'll see you on Monday. Have a wonderful weekend.